I'd like to welcome everybody to the December Canada Wildfire webinar. I'm really excited. Today we have Chris Stockdale and Leo Fred talking to us about Burn-P3 Plus, a new multi-model fire simulator based on Burn-P3, and it fits really well into our webinar schedule. So we had introduction and basis of modeling last month that set us up really nice, as well as the CIFC meetings. So the timing is perfect for this presentation, and I'm very excited. So today I'm coming to you, as is Chris, from Treaty 6 territory. I have a little bit of history about Treaty 6. So Treaty 6 was signed by Crown representatives, the Cree, Assiniboine, and Ojibwe leaders on August 23rd, 1876 at Fort Carleton, Saskatchewan, and on September 9th, 1876 at Fort Pitt, Saskatchewan. The treaty boundaries for Treaty 6 extend across central portions of present-day Alberta and Saskatchewan, including Leduc and Leduc County, where I'm located, and Edmonton, Alberta, where Chris is located. So I'd like us all to take a moment and think about the places that we live and who may have lived here before and cared for the land before we happened to come. And with that, I would like to hand over the presentation to Chris Stockdale. He's going to be our presenter today. He's coming to us from the Canadian Forest Service, Northern Forestry Centre. So welcome, Chris.
Thanks very much for the introduction, and thanks for having us today. I am sharing this presentation with Leonardo Frid because the Burn-P3 Plus modeling system is something that is built upon the SynchroSim modeling platform, and Leo is the creator, well, one of the creators of the SynchroSim platform, and understanding what SynchroSim is capable of is just as important as understanding what we're doing with Burn-P3 Plus. So we'll get into it here. I've listed the project team that's been responsible for the development of this over the last several years. And without further ado, we'll just carry on here. And first, I'd just like to give a bit of background on Burn-P3, which was developed in 2005 by the Canadian Forest Service, that provided kind of the impetus for what we're working on today. And the reason we've called this new system Burn-P3 Plus is it's capable of doing the things that Burn-P3 did, but a lot more. Burn-P3 was built upon the principles of the CFF-DRS, and as such, it uses the FBP and FWI systems to grow fires in a deterministic process using the Prometheus fire growth model. It's essentially a batch processor for sending instructions to Prometheus, telling it how many fires to burn, what the cause of ignition was, what time of year it's burning, where it should start, how long it should burn, and under what weather conditions. So in so doing, the model inputs and outputs give us valuable information on where fires are likely to start, where they'll go, and how burn likelihood varies both throughout space and time. While most users have tended to focus on the final burn probability map, the model produces a lot of different outputs that allow you to answer numerous questions about the wildfire environment. What you see running in the background here is kind of a simulation of a Burn-P3 run that essentially kind of just throws a whole lot of fires on the landscape. And as you see, parts of the landscape get darker and darker red as you find where more and more fires overlap with each other. A really important thing to note with this too, though, is what you see in the end, these dark red areas. The dark red area is not where fires are most likely to be contained, but the dark red areas essentially are indicative of kind of intersections. Think of busy traffic junctions in the city. This is where fires tend to move through, where they may start from, where they may end up. But where the fires begin, their whole pathway, those are the things that can vary considerably. The process of the original Burn-P3 model starts with choosing the number of iterations, choosing how many fires are going to burn in a given iteration of the model. So this is something that you can usually comes from historical records, but the user can choose any number they want here, or even just a single fire per iteration. Next, for each modeled fire, the user provides either a distribution or an absolute number of days that the fire will grow for. So this again comes from some possibly historical information, or you can make up any distribution you so desire, depending on what the objective of the modeling exercise is. Then the season and cause are determined, which then breaks down, the likelihood of, is it a human caused fire? Is it a lightning caused fire? Is it burning in the spring, fall, summer? You can break up the seasons as fine scaled or as coarse as you like. You can ignore seasons. You can ignore the cause too, if you so desire. It then, based on that information, and you do some analysis of historical records, or you can choose to actually tell the model where the fires are going to start, is going to draw from spatial distributions to determine the actual location of a fire ignition. Then it chooses the weather conditions for each day of the fire simulation and the number of hours per day. So once it has done all of these things, it then sends the information to the Prometheus fire growth model. The fire is simulated, the fuel grid is reset to its original state, and the process repeats as many times as the user desires. So years ago, due to competing speed, and of course my phone rang right then. Years ago, due to computing speed, 5 to 10,000 iterations were often done, but many users now run the model well into the hundreds of thousands or even million iteration. It's a data-hungry model. There's no getting around that. And what you choose to use as inputs has a very significant impact on the outputs of the model. In the classical mode, or the mode that most people are most familiar with, as described in the user manual, which we are in the process of updating, you essentially replicate the fire regime and determine the annual burn probability. But in the last 10 years or so, people have become much more creative with how the model's being used, which allows us to test a lot of different scenarios. The model is only capable of simulating conditions that you allow it to run. So it's not the fault of the model if you give it unrepresentative inputs or limit what it can do and then compare to real world events that are not within those boundaries. It's important to validate and evaluate the numerous input parameters that are fed to the model. It can only produce outcomes within the boundaries of what you put in, as I've already said, and therefore these inputs are themselves very important and informative pieces of information. This should be transparent so that everyone understands what the appropriate scope of inference for any given model run is. In this review paper from 2019, we identified more than 130 peer-reviewed publications using Burn-P3 and other burn probability models, and there are innumerable unpublished Burn-P3 projects that have been created by land managers and researchers. What should be very clear, though, based on how many studies there have been done, is that there is no kind of standalone one way of running the model, because it really depends on what your outcomes that you're trying to achieve are and the objective of the modeling exercise itself. It's really helpful to see Burn-P3 as a modeling framework rather than a model itself. It's a research tool that can be applied to many different types of problems. At its most basic, the Burn-P3 system, it combines weather, ignition locations, and length of burning periods to produce outputs pertaining to fire perimeters, both final and daily perimeters, ignition locations, burn probability, and other FBP outputs such as intensity, rate of spread, and others. How you use these outputs depends on the goal of your analysis, and therefore your inputs need to be chosen to reflect these outputs. At the same time that we wrote that review paper, we identified numerous things that the user community thought could use improvement. Speed was the primary barrier to using Burn-P3. Even on powerful desktop computers, a 50,000 iteration run of Burn-P3 could take weeks. Also, as users have become more and more creative in how to use Burn-P3, its limited flexibility was flagged as something to improve. It was built as a fully contained system, so you load in all the data, hit run, and wait for the final outputs. Setting up individual scenarios was tricky and is labor intensive, as each Burn-P3 project is a single scenario. There's no way to have changes made in, say, a baseline assessment cascade through subsequent scenarios. Its lack of speed and flexibility also led many users to only focus on the burn map produced at the end of the process and not bother to dig into other outputs at all. So when setting out to rebuild Burn-P3 to be more modern, there was a strong desire in the user community to make this model more flexible, faster, modular, fire growth model agnostic, integrated with other types of models, to be able to interact with R and Python, and to be open source and customizable. In so doing, we landed on partnering with Apex RMS to help us develop Burn-P3+. So at this point, I'm going to hand off to Leonardo Frid, one of the principals of Apex RMS, to give a brief overview of the SynchroSim modeling platform.
Thanks, Chris. Yeah, so as Chris mentioned, I work with Apex RMS, and we're a small company of ecologists, data scientists, and software developers. And we, based on our experience of many years of developing ecological models, we found that often we were reinventing the wheel. And there are many aspects of ecological modeling that are common, independent of the type of model that you're using. And that was the motivation for us to develop SynchroSim as a framework for developing, running, and exploring spatially explicit simulation models. SynchroSim has been around for about 10 years, and there are hundreds of registered users. And because of the support of various public agencies, both in the US and Canada, and NGOs, the software is available for free download. Next slide. So SynchroSim was kind of ideal for this project in developing Burn-P3 Plus because it is specifically designed to connect different types of models together. And as Chris mentioned in his introduction of the way Burn-P3 works, it's a series of models that are connected together. And these models can either be in script form in R and Python, or C# or other scripting languages, or they can be in the form of existing executables such as Prometheus. SynchroSim is also built to automatically help people with Monte Carlo simulations, which is, again, a very important part of Burn-P3 Plus. When you create a model for SynchroSim, SynchroSim automatically structures both your input and output data. And every time you run the model, it creates a timestamp of all the inputs that were associated with that model run. So you can be able to connect, what were the inputs that led to the particular outputs that you're observing. It's also designed so that the modeling code itself is in a Git repository, so you can be able to easily track what's changed between versions of your models. Next. And SynchroSim comes with different interfaces. So there's a full command line API as well. There's a graphical Windows interface that's kind of designed to help decision makers explore the model. And then we've developed some R and Python packages. So everything that you can do from the Windows interface, you can do in a scripting language such as R or Python. Next slide. It's designed to scale to large landscapes and many Monte Carlo realizations. So we have some example use cases of SynchroSim models, for example, that have been run across the continental US at 30-meter resolution. And so the framework is designed to help you with multiprocessing, both using spatial tiling, if you would like to do that, and also multiprocessing across Monte Carlo realizations. Next slide. So as I mentioned, we have a graphical Windows interface, but we also have next an R package called RSynchroSim, and next a Python package called PySynchroSim. Next slide. So a little bit of the architecture of SynchroSim. So SynchroSim packages can be developed by anyone. They're usually published in a GitHub repository, and they're submitted to us, sort of similar to the process of submitting an R package, say, for example, to CRAN. And then once approved, the packages are then hosted on a SynchroSim package server. And a modeler running SynchroSim on their desktop can download SynchroSim packages, and then they develop data sets, which are called SynchroSim libraries for a particular package, which helps them store all of the model inputs and outputs. Next slide. I think this is my last slide on one more slide on SynchroSim. Yeah, so and what is the SynchroSim package? So we have a large number of packages. Here are some examples. Burn-P3 Plus is one of them now. And so a package is really a wrapper around modeling script or code. And it also includes, on the right, you can see the structure of package, typically an XML file that describes the structure of your model inputs and outputs data. And also, there's the option of including that YAML file as a conda environment so that you can, when somebody installs the package, they also get the entire environment. If there's other software dependencies, for example, having the right version of R, having the right version of a particular R package, such as Terra, that gets installed with your software. So you don't get into this issue of packages not being able to run if you don't have quite the right environment on your own computer. I think that was my last slide, Chris.
Thank you very much, Leo. So this is looking at the Windows interface of the Burn-P3 Plus package. And what you like, so Burn-P3, as Leo has described, Burn-P3 Plus is a package that runs on SynchroSim in kind of the same way an R package runs in R. So this corner here that I outline in red is kind of the library or the database explorer pane. So in this particular example I'm showing you here, I've got two different libraries loaded, one for the Banff National Park and another one for Glacier National Park. In the Banff National Park library, I've set up 8 distinct scenarios to be run. Each one has a unique name. So they can be run individually, or they can all be selected and put in a queue, and they will run one at a time. Like one will finish and then it'll move on to the next one. So it's a nice way to kind of load up a bunch of scenarios, hit run, walk away, and wait for your answers. On this right-hand side, you're seeing kind of the properties for a specific scenario. I'm not going to go into tons of detail on this, but what I'm just trying to draw attention to is here you can enter a detailed description of the scenario itself and where you make many key decisions and choices for what you want the model scenario to do. Creating new scenarios is really easy. All you have to do is cut and paste an existing scenario, and then you can make changes, any changes you want in the new scenario that you've just created. And it'll have all the other inputs in it that were in the other scenario you did. You can also make scenarios dependent on each other so that changes made in an upstream scenario will cascade through other scenarios you've created. You'll have to rerun them, but just, they'll be set in queue so that if you think, oh, my base one is, I want to change whatever, the fuel grid and the whole thing, it could cascade that through your whole system. You just have to rerun each individual scenario, but that it'll track that for you. The various tabs across the top of that window that you're looking at are where you'll find all the different places where you're going to load in spatial data or numeric tables, or importing rasters, CSV tables, or you can fill in tables manually just by typing in some of the boxes. And in the bottom left, and this is something that I really, really enjoy about working with SynchroSim, is where you can load and view the outputs of the scenarios you've run. Burn-P3, like the old version of Burn-P3, just produced everything through a whole bunch of TIFFs into, and a few tables into some folders on your computer, and you then had to build your maps. You had to choose your color schemes, etc. This allows us to set some defaults. You still have the ability to do anything you want customizably with your outputs. They are there in a folder for you to play with, but this provides some good defaults that you can do. So here you can see the outputs created from 3 of the scenarios. In this particular case, I've arranged it. Each row is a unique scenario. You could set it so that the columns are the scenarios. In this case, the first column is showing the input fuel map that was chosen for the particular scenario. And then the next one is showing the mean annual burn probability. But then we break the annual burn probability into its seasonal components. So you're seeing the spring burn probability in the 3rd column and the summer burn probability. In this case, the top 2 rows are comparing different fuel maps, both using the Prometheus fire growth model. And the 3rd row is a scenario using the same fuel grid as the 1st row, except it's using a different fire growth model called Celtifire. I'm going to talk more about this as we go through. So what you can also do is you can zoom in and out on any one of the maps in this viewer. And as you do so, it is going to zoom in on all of the maps in that viewer. So you can make comparisons to, all these different maps you're looking at. You can create your own maps here too, if you want. So you can visually compare your outputs in the same location across all your scenarios. In addition to maps, charts can also be created, and SynchroSim supports the ability to create all sorts of different output charts and tables. I'm just showing you a few very brief examples here. So as I described in those scenarios, we have the ability now to work with multiple fire growth models in Burn-P3+. Some models are faster than others and provide different functions and outputs or require different inputs. Currently, we have 2 models wired in, and those are Celtifire and Prometheus, but we're working on Firestar, and we're also looking at incorporating Wise, which is kind of the updated version of Prometheus into this. The modular nature of SynchroSim permits the inclusion of any future fire growth models as well, without having to change all the other code in this. This figure shows a comparison between Prometheus on the left and Celtifire on the right. They produce very similar but not identical outputs using identical inputs and parameters. The reason for the slight differences is Celtifire is a cellular fire growth model using an 8-vector spread sort of mechanism, whereas Prometheus is a full vector-based model. So they give slightly different outputs. Cell-to-Fire, however, operates much faster than Prometheus, but it isn't providing secondary outputs like intensity or rate of spread. However, because of the modular nature of SynchroSim, we can write code that will calculate those things afterwards, and we will be working on this in the next few months. The cool thing with this, though, is because the Cell-to-Fire's speed advantage is it allows a user to test their inputs and settings and see how it's playing out on the landscape before they maybe want to commit to a slightly slower run to get more detail out of Prometheus. And that is a really cool thing. Just a brief reference to Cell-to-Fire is a model that was created by Cristobal Pais, and the authors here are indicated in the top right. And this is kind of showing its similarity of fire shape that it is producing Prometheus fire growth model output on the left and a Cell-to-Fire output on the right. As I was describing, it's an 8-vector spread model, and part of the reason we see slight differences in the total outputs is an 8-vector spread model doesn't quite do as good a job at producing an elliptical fire head as a vector model. If we were to move this to being a 16-vector or 32-vector model, it would certainly improve that considerably. So under kind of high wind speed conditions, you get quite long, pointy-looking fires out of Cell-to-Fire, just something to be aware of. This is comparing the old Burn-P3 system to the new Burn-P3 Plus system using the same input data, the same number of iterations, and running the same number of fires. So Burn-P3 Plus executes the run in about 20% of the time that the old system did. So this is just having SynchroSim manage Prometheus compared to the old software version from 2005 managing Prometheus. So we've realized a 5-fold increase in time just with this. So coupled with the previous speed advantage that Cell-to-Fire shows over Prometheus, we're now looking at, roughly, it varies by run, but that's why I have the approximate numbers here, 60 minutes to 12 minutes. But we're seeing now kind of order of magnitude increase in speed, 30 times. Like if you're using Cell-to-Fire in Burn-P3 Plus, it's going to give you outputs about 30 times faster than the old Burn-P3 system did. So if you're thinking about an old run that used to take 2 to 3 weeks, perhaps to produce outputs, you're going to have those same results now, same day that you ran them. This also ignores the scalability of installing Burn-P3 Plus on high-performance clusters or cloud system to go even faster. So instead of sitting for weeks to complete a single run, we can now crank out numerous scenarios in the same day or even over a weekend. I'm going to hand back to Leo now to describe yet another innovation we've implemented in the Burn-P3 Plus framework, which includes being able to now model through time and incorporate vegetation succession and ways of being able to share projects online with other users.
Yeah, thanks, Chris. So one of the motivations for this part of the project was to be able to help people look at not just a single point in time burn probability, but to be able to model the interaction between fires and vegetation succession and change over time. And so to do this, we created a package that connects 2 SynchroSim packages together. The Burn-P3 Plus package with a package called SynchroSim, which is probably the most popular SynchroSim package. It's a landscape modeling package that projects changes on a landscape over time, and it's really agnostic to the kind of landscape. It's got a broad range of existing applications. I think there's over 50 peer-reviewed publications, and it's been used to look at ecosystems ranging from coral reefs to boreal forests. So in this case, again, the motivation was to help include fires generated using Burn-P3 Plus within SynchroSim simulations. And this is also one of the packages that is available on the SynchroSim package server. Next slide. So the way the package works is you're running an SynchroSim simulation over many years. SynchroSim has as inputs your initial sort of vegetation fuel map, rates that you may want to apply. So depending on what scenarios you may want to apply, you may want to have scenarios that look at sort of fuel treatments and locations where you want to apply them, and how much of the fuel treatments you want to apply, as well as the rules as to how vegetation changes over time. And so SDSIM will run for a time step and generate an updated fuel map based on the events that have occurred on the landscape, either fuel treatments or natural disturbances, and then supply that updated fuel map to Burn-P3 Plus. Burn-P3 Plus having information that is static, such as the elevation map, weather zones, a distribution of ignition locations, and so on and so forth, will then grow fires based on that fuel map from SDSIM and provide the fire occurrence map to SDSIM, which will then again apply things like changes to the vegetation based on where the fires occurred, as well as updated information based on fuel treatments for the next time step. And so that cycle continues for as long as you want. And of course, both models having stochastic elements in them, you would also want to run this whole process for many Monte Carlo realizations. Next slide. So here's again one of the key screens for this particular SDSIM Burn-P3 Plus package, where you specify as an input the Burn-P3 Plus library that is kind of your template for your landscape, containing all of the static inputs. And next, you also specify the linkage between the two models is the ID value specified for different vegetation types or fuel types. Next. And so that fuel attribute that we're going to supply depends on two things. It depends on the sort of the vegetation class associated with this particular simulation cell, which can change, and also the age of that vegetation class. So for this very simple example, we just have the vegetation class representing a particular fuel type, but then depending on the time since fire or fuel treatment, if it's been less than or equal to 2 years since a fire or fuel treatment, we apply a non-fuel type ID, and otherwise we apply the fuel ID associated with that vegetation type. Next slide. So here's some example outputs where you're seeing now a landscape changing over time. On the top, we have the occurrence of the fires generated by Burn-P3 Plus. And then on the bottom, you have kind of the resulting fuel ID based on where those fires occurred. There's a couple of things. Next slide. So you can see we're just tracking this individual fire, which occurred in the very first time step. And underneath, you see as a result of that, the footprint of that fire remains as non-fuel for the subsequent 2 time steps. And then again, as in this simple example, we modeled, succession after 2 years, a return to the base fuel type on the last panel on the bottom right. And yeah, so I just also wanted to say a couple of things about SDSIM itself. So SDSIM uses this approach called state and transition simulation modeling. It was originally developed in the early 1990s to model large landscapes in the United States that combine both forest and rangeland types. And again, there was this need for a more flexible landscape level modeling approach. And it's been, as I said, applied to a very wide range of different ecosystem types. Next slide. If you're interested in learning more about the methodology, there's this publication from 2016 in Methods in Ecology and Evolution, and a very sort of quick description of the approach over the next couple of slides. So next slide. So the state and transition simulation modeling approach, you begin with a landscape and you want to next classify that landscape according to some classification scheme. That classification scheme is completely flexible and is going to depend a bit on your modeling questions. So obviously, for linkages with Burn-P3 Plus, the fuel type of a particular vegetation would be one of the key reasons that you would include in this classification. Next slide. You also track ages, as I mentioned. Next. And then you need to develop some kind of a conceptual model of how a particular location of that landscape might change over time, and the different processes that are going to drive change for a particular location. Then you assign rates to the different processes. Next slide. And then you can track the changes in that location over time. Next slide. And if you apply that to the whole landscape, you're tracking changes for the whole landscape. Next slide. Now, because the process is stochastic, again, we run many Monte Carlo realizations. And so at the end of the simulation, you get not just a sort of a fixed estimate, but you also get a range of uncertainty around your projections for a particular landscape. Next slide. And so ultimately, at the end of the simulation, then you produce, or there can also be interactions between simulation cells. So in this case, next slide, the application of fires on the landscape for the connection between SDSIM and Burn-P3+ can come from Burn-P3+. If you're not using Burn-P3+ to generate the locations of fires, next slide, then there are other approaches like supplying sort of a predetermined burn size distribution as an example. And I think that might be the last of my slides, Chris.
No, you were going to lead into the online stuff.
Oh, yes,
too.
of course.
Yeah.
Okay. So, yes, so one last thing, and I think the deck got a bunch of slides included, so you may need to skip forward here because there's some repeats.
My bad. I thought I deleted those.
Yeah, so the last thing I just wanted to mention is another aspect of SynchroSim is that it allows you to publish your models to the cloud. So I showed you the SynchroSim desktop software here, where you're running the software on your desktop with different packages, and you've got your data sets as SynchroSim libraries. Next slide. And those packages can be hosted on a GitHub package server. Next. But we also have a version of SynchroSim that runs on a server, so a server version of the software that again can up on an application server online. You can have SynchroSim data sets, libraries, and obtain different packages for running different models, such as Burn-P3+ on that server. Next slide. And then connected to that server, we've created a web interface, so you can interact with SynchroSim on the cloud via a browser. And using that browser, you can upload models that you develop on your desktop to the cloud and essentially publish them. Either they can be published privately, so you can share them with selected users, or they can be made publicly available. And so right now, those published models, people can go online and review your model results, and they can download your models if you choose to make them available and run them on their desktop. And our goal is eventually to actually be able to run the models on the cloud and take advantage of sort of cloud infrastructure for being able to run very large simulations, for example, and be able to collaborate on model building on the cloud. So the sort of the ability to run on the desktop would become optional. Next slide. So you can go online to cloud.synchrosim.com and check out some example publications of different types of models. And these models are, there's a couple of Burn-P3+ examples up there, but there's also examples for other modeling platforms as well, including SDSIM models. And I think that is really my last slide now.
Thank you very much, Leo, for that. So this right now, I'm showing kind of a definition of wildland fire risk. And of course, if we were to ask 7 different wildfire risk researchers for a definition and an equation for wildfire risk, we would get 7 different answers. However, they all contain the same basic elements. Sometimes words are changed a little bit. It just kind of depends on which ones you put in which order. But what I'm mainly wanting to draw attention to is that Burn-P3 Plus and Burn-P3, the old version too, really focus on the right-hand side of this. They deal with the hazard component, which is the combination of the spatial and temporal likelihood of fire combined with its magnitude. Magnitude is usually its intensity, but depending on the application, it could be, say, rate of spread or something else like that. But because of the modular nature of Burn-P3 Plus and SynchroSim functionality, it now provides the space and a framework by which we can start using existing models of exposure and susceptibility and even create new ones in order to provide more fulsome measures of wildfire risk. So I'm going to go through kind of a summary of the main differences between Burn-P3 Plus on SynchroSim and the old version of Burn-P3. And those are, first off, starting with the old version was quite slow. It was built almost 20 years ago now. So we're now seeing, just using Prometheus and Celtifire on the existing system, we're now seeing roughly 5 times speed realization for Prometheus itself, and then another 6 times faster using Celtifire. So we're now talking kind of in the 30 times faster than the old version of Burn-P3 if we were to be using the Celtifire outputs. Now, again, this, as I previously described, doesn't include the scalability component of being able to run this on high performance clusters or cloud systems where we can get even faster than that. And also is not including some newer fire growth models that we intend to bring on board, such as WISE and Firestar, that we're currently kind of investigating to see how we can put these in there. And that will get us going even faster. So, the old version of, waiting weeks and months for outputs, hopefully now we have you down into being able to do this within hours and days. And that is a massive improvement, especially being able to run lots of different scenarios. The old version of this was fully contained. That is, it was a Windows executable. You open it up, you loaded all your information, you hit run, and you had to wait for it to finish everything. The new before you could look at any outputs. The new system is modular, and it is also expandable. Showing the ST-SIM component was just one example, but once you learn how to work with SynchroSim and the various components of the system, you can add in other models at will to this system. The old version only ran on Windows, whereas now we have the ability to run Windows, Linux, or cloud simulations. The old version also had no integration with R or Python, and now we do have R and Python integration. We've moved away from purely graphical user interface. There still is a graphical user interface, but now you can also operate this whole system from R or Python. The old version too had no database structure. You stored all your inputs in a given folder on your computer, and as you set up the Burn-P3 simulation, you would tell it where you wanted it to put the outputs, and it would store them there. But if you wanted to share a project with someone, you had to find where the inputs were, where your outputs were, where the project file was, and put them all together, and then try to send them over to somebody else to set up the same thing. But they would still have to set up their own run with those things, point at where they'd stored them on their computer, whereas the new system provides a database. The library is what it's called in SynchroSim, of all your inputs and outputs. So it's very easy to package and send to different people. And as Leo just described, that this can even be done online. The old version, the source code of the whole system was locked, so you really couldn't make any modifications to the system, whereas now the Burn-P3 Plus component has full GitHub integration. SynchroSim is a proprietary piece of software, but as Leo had said, it is freeware, so it's free for anyone to use. And the add-on components, the packages themselves, are open source, so there's GitHub integration there. The old version as well could only do a full run. You had to choose all your conditions, and you had to run it from start to finish. And if at the end you realize, oh shoot, I really wanted to have my fire intensity map, I'd like to produce a fire intensity map, you have to start the whole system over again and wait for it to run again. Whereas now the Burn-P3 Plus system, we didn't talk a whole lot about the pipeline concept of Burn-P3 Plus, but we can ask more questions later about that. But it's now possible to break up runs. You could just set it so that all you do is create the table of where all the fires start. And you could just leave it at that, and then you could do an examination of that to do some filtering, edit that how you like, and then feed it through to the next step, which may choose the season or the weather conditions associated with the fire. You can then structure that. So what this does, though, with this pipeline concept of being able to break up a run, is you could set a whole number of fires on your landscape, and then you could say, okay, well, as you scan through this table of fires without having to wait for the fires themselves to be run, as an example, you could say, well, at a certain BUI threshold, I would like to change some of these areas that are currently indicated as non-fuel in my fuel grid, say they're wetlands, at a certain BUI level. I think those should actually become burnable. So what you could then do is take this whole table of all the fires it's going to run with their associated weather conditions, and break that now into two separate tables. One, you say using a BUI threshold. So you can have a low BUI threshold where a certain area is treated as non-fuel, and a high BUI where the certain areas that were non-fuel are now being treated as grass or whatever fuel type you so choose to put in there. And now you can set this up as two separate scenarios running on two independent fuel grids, and then combine your results at the end. And the possibilities of the edits you can do in the system are endless. Furthermore, the old system was a single scenario per project. So if you set up an old Burn-P3 project and they say, okay, now I would like to set up a scenario where I'm going to put in some fuel treatments on the landscape, you have to start at the very beginning and load all your data again, set up a new scenario, and hit run and wait for it to produce the outputs. Whereas now you have the ability to create the original scenario, copy paste, set the second scenario, and just change whatever input you so desire on that. As I had sort of already described, the old Burn-P3 could only use a single fuel grid per project, but now it is possible to use multiple fuel grids per project or even within a scenario. The old system also had independent draws for all the inputs. So kind of as I was showing the process diagram of choosing the number of spread event days, choosing the number of fires, choosing the weather conditions, choosing the hours of burning, those were all independent draws from each other. And sometimes that makes sense, but sometimes that may not make sense. I mean, you might want to say, well, you know what, in really high BUI conditions, it doesn't make sense that the hours of burning are really low. In like super BUI conditions, we should have longer spread event days. We should have more hours of burning. You can do that post-processing now to be able to make that happen. The old system also required all of the input to be prepared outside of the model. So you had to create all your outputs, structure them in the way that Burn-P3 was going to read them, and then you could run the model. Now, even though it still does require that, they can be developed within the model in the sense that you could write a new transformer within SynchroSim to do some of that processing. So you could write a transformer that is going to go and clip out a fuel grid and extract the weather and so on, and then just build some of your inputs all within the same thing. Previously, too, all the post-processing was external. So it would spit out your various tables and your TIFF files or your ASCII files, your rasters into a folder, and it was up to you to use a GIS system to put all that together and analyze it and make the maps. We've now set up a significant number of post-processing defaults that have been provided, and this is fully expandable. We can add in things. The great thing about this whole GitHub concept with Burn-P3 Plus is, just as an example, the post-processing element of this is one of the transformers in the system. That is actually just an R script. You could go into that R script and add in new outputs that you would like. There's a couple of things you have to do to make sure that links back into SynchroSim so it feeds it back into that output display window that we were looking at before. But the thing is, as the user community comes up with new ideas, new ways of analyzing the data, new ways of producing or visualizing the data, you can put that into the GitHub stream, and that then becomes available for all other users, which is a fantastic way of like community building this model. And as I've already kind of described, the concept of being able to break up runs using the pipeline, and also the old one had no ability to integrate with other models, whereas now, because of this pipelining process, it's entirely possible to introduce other models. Leo has just shown the ST-SIM model, which shows how vegetation succession after fire might occur. But you could also just, as concepts that I've been thinking of that I haven't started yet, but that I wish to continue doing work on, you could set up so you do a certain number of Burn-P3 iterations, evaluate the landscape, look at where things are, kind of identify your fire sheds, identify your most common fire travel pathways. You could then feed that, say, into a fuel treatment model that evaluates those inputs and determines where it should put a fuel treatment. Feed that back into Burn-P3 to see, how did that change my landscape susceptibility to fire? You could set all sorts of rules. You could evaluate suppression systems. You could evaluate anything that you so desire to write a model for and include in this system. So some final thoughts, and over on the right-hand side is a QR code that you can look at that will take you to the Burn-P3 Plus GitHub homepage, which has some information on getting started with the model. We are working on more training materials, so please bear with us, but that's coming, and I will talk more about this in a few slides. But what I want to stress is that Burn-P3 Plus is not a fire growth model. Burn-P3 Plus is a thing that sends instructions to a fire growth model. But really what this is, it's a sandbox to help you understand your fire environment. You can play with inputs, you can visualize those inputs, you can visualize the effect of changing your inputs on your outputs, and you can share that online with other people. So what this is really designed to do is to interactively plan scenarios, to organize and visualize all your inputs that are going into the model, to build the instructions that you send to a fire growth model, execute those fire growth model scenarios, collate and visualize all your outputs, and to be able to share that project with stakeholders and partners, and to then be able to make changes to the project, or they can make changes to the project and run it for themselves and play with the input-output relationships. So like, there's no recipe to this system. This is a, I don't know, you can use a bad analogy. We've given you a kitchen now. You can make whatever you want in this thing, the relationships, the spread event days, the weather you choose to model, the fuel grids you choose to model, any of this can go into this system. So the next steps, and this is the final slide in this, is the next steps in this is we are in the process of developing a training course that we hope to be able to share with the public in the spring or summer of 2024. We are running a crash test dummy version of the course at February for some internal users. And I'll be reaching out to a few people to help us test this system in late February. And those materials that we create, we will then be tailoring to be kind of self-learning materials. So for those who can't travel to attend a training course or don't have the funds to attend a training course, we'll be turning this into self-learning materials and have a couple of online tutorials in place already, but we will be developing several more of these. And with that, I would just like to conclude and happy to take some questions. And I think we've got a significant chunk of time for that.
Thank you, Chris and Leo. That was amazing. I'm quite frankly a bit blown away here. And I received a private message. I'm going to read it to you. And it says, it seems like you actually changed it to what everyone has wanted, and that typically never happens. So I scribbled down 6 or 7 questions or things that I thought would be great during your presentation, and every single one of them you have answered. For example, I was incredibly impressed with the ability to include multiple fire growth models. The pipelining or breaking down runs, I think, is going to be game changer. And I am looking at this and my brain's just going that this is going to be like a graduate student researcher or a planner in government. This is going to be a dream come true for them. And I'm very thoroughly impressed. So kudos to you guys. What an endeavor to put this all together. This is a question that I did have, which I believe you answered with your upcoming training modules, but are there intentions to put together a sample data set or control data set for people to practice or run internal training or validation on?
Good question. And if you go to that, if you scan that QR code, it will take you there. And as you download, there is a simple exercise that you can go through. And the exercise really is just to ensure you've got all the components, because there's numerous components of this, like software components. It's just to make sure you have all the required software components installed right. Can you make the whole system run properly? Like, do you get answers? Because if you do, then you've got everything installed right. And then there's 2 or 3 different template libraries that you can kind of play with to see how they're structured. And then you can kind of play with the model there. Now, validation is in itself a really interesting question. So with validation, I think it's really important to note that validation is a pretty complex thing, and we need to be really clear what we mean by it. So usually validation is kind of just a check of the outputs of a model compared to what happened in the real world. Sometimes you get a good fit, sometimes you don't. But all model runs should include sensitivity analysis, and you should also be really openly disclosing the inputs and the model settings chosen, because the first questions you need to ask yourself is, if the outputs don't match real world events, is you have to ask yourself, were the real world events even possible within the range of conditions I gave the model? The model can only produce what you tell it to produce. So if you set boundaries or limits on what the model can do, and then you try to compare to things that happen in the real world that you never told the model it could do, such as a common setting that people have over the years used is, well, it's really easy to put out fires in grass and deciduous stands, and therefore, what we're modeling are escape fires. So I'm going to not let the model start fires in grass and deciduous because those would probably get caught by initial attack. But if your real world event is a fire that started in grass or deciduous, you can't really compare the two events anymore because you didn't let the model do that. So how can you compare a real world event where they didn't get that in initial attack? So you need to do some significant evaluation and testing of your fundamental questions there. The other thing too, though, is the validation concept is, because this is, as a kind of the metaphor I was using, this is now a kitchen. It's not a recipe. It's a way to play with whatever combination of things. Any validation exercise, an evaluation exercise is going to be quite unique to the question you're trying to ask. So if you're trying to, like, regardless of what you're trying to do, you really need to make sure that the inputs that you've chosen are representative of the outcome you're trying to achieve.
Thank you. Thank you very much. We have another question here in the chat. So for anyone else who has questions, please post them in the chat box and I will read them out. You've answered this somewhat, but I'd still like to bring it up because I think it's a really valuable question. So is there a script or module to add a completed impact analysis raster layer based on landscape values at risk and integrate Burn-P3 Plus to run and create a cumulative wildfire risk modeled run, or would that be a separate GIS exercise outside using Burn-P3 Plus output?
There isn't an existing model or module or transformer to do that right now. You could do that externally, so you could use the outputs from this and then, you know, build your own thing in GIS. But because of the modular nature of SynchroSim, you could write that as a SynchroSim transformer and include it and put it into the system. It would become what we would call a Burn-P3. So the Burn-P3 Plus system as it is actually 3 components. There's, well, ignoring SynchroSim, so it's 4. I mean, there's SynchroSim, which is the base thing that it's all running on. Then there's the Burn-P3 Plus package. And then the Burn-P3 Plus package is talking to the Prometheus add-on package or the Celtifire add-on package. So you could add on yet another add-on. You could add on a impacts package, or you could add on a exposure package, or like, etc. And then you can set it up and you create your pipeline. So, you know, like the output of one feeds into the next one. So it does allow you to do that, but you would have to be the one to create that yourself.
Thanks, Chris. I have another question here. This person is curious about the confidence around assigning fuel types to forest stands of various composition, successional state, and recent disturbance. Is that process fairly well understood, or is it an area of active research?
Well, it's definitely an area of active research. There's all sorts of research going on across the country in terms of doing a better job of trying to build fuel types and relate fuel type to vegetation structure. Now, of course, that is one of the largest weaknesses in the FPP system overall, is breaking, you know, the entirety of Canada's vegetation structures down into 16 individual fuel types, with, you know, some of them being highly variable, like the deciduous, or sorry, the mixed wood, or the M3, M4, which is the spruce budroom kill categories, which have increments of conifer content in them. But that is also the process of the CFF DRS, the next gen CFF DRS system that is also underway within NRCan. And when modeling systems are available for that, this system just allows the new model to be inserted into that process. So
thank you for that. That was also noted in the chat that the next generation fuels will address some of these concerns.
Yep.
I'm curious if there are any future thoughts for how to help facilitate or support wildfire management agencies or research groups to work together and leverage for cloud computing and sharing of their models moving forward.
I think that would be the best. Well, so in terms of the concept of it, I mean, the structure of SynchroSim is quite capable of supporting that. In terms of official organizational, I mean, the way we built this now is it's much easier to share projects and work collaboratively on things because you can share and visualize the same inputs by loading it onto the SynchroSim cloud server. However, in terms of running it on the cloud system, I think I'm going to hand that question to Leo at the moment because it really is much more about a license. Like, I'm not entirely sure on the how to run it on the cloud. I just know it's possible to run it on the cloud. Leo, do you have more to add to that?
Yeah, I could speak to that. So as I said, the SynchroSim cloud system is quite new. We actually just put out, we're still calling it beta, and right now it's really a way for people to publish their model results and to be able to download other libraries that people have created. We're still running the model. When we do big runs, we either run them on a desktop computer or we run them on a virtual server using a product such as AWS, or you can run them on an HPC as well. But there's no kind of cloud or web interface to these cloud computing resources right now. The idea is that eventually, yes, that the cloud version of SynchroSim will have a web interface that would allow you not to just view model results, but actually set up model inputs and run the model. So that'll hopefully be coming out in the next couple of years. And part of that process too will allow, like right now we're hosting that version of SynchroSim on our own servers, but the idea is eventually there would be some form of licensing that would allow, different agencies, if they want to host some aspect of the tool, either the data or the actual server that's doing the runs on their own system, that would also be possible eventually as well. Chris, does that answer the question?
I think so. Does that answer, Karen, back to you? Does that answer the question?
Yeah, that's great. Thank you so much. So we're having a bit of a discussion going on in the chat right now regarding kind of a sweet spot or optimum number of runs. The initial question was, if I'm running 100,000 iterations, do I get diminishing returns around a certain number of runs? And there's some comments back and forth about how this is a topic of debate right now, looking for when it stabilizes. Do you have anything you would like to add, either Chris or Leo?
I mean, the way it was done in the past, and you still kind of have to do the same thing with this, is you could take your out. So the old Burn-P3 system would give you a table that would give you kind of the, like the mid, it would track a few statistics as like, okay, and I can't remember the number, but like just as an example, say every 1,000 iterations, it would compute a statistic. And then you'd be watching that, like it's kind of the general, like the average change in burn probability across the whole landscape that you're simulating. And then as more, like you'll see significant changes early on because fires are happening in unique places where they haven't happened before. But as kind of the patterns start to repeat themselves, that starts to diminish. So you're kind of plotting it as a asymptote and you start seeing where does that line start leveling off, and then you kind of choose that. So that actually is kind of the point of what I was trying to get at with why including cell to fire in the system helps, because the old way is like you still had to run it forever to find out when you had to stop running, and you'd only evaluate afterwards and say, well, okay, I need more. Or you might say, oh, I only needed half as much as I ran. You don't get that time back if you spent twice as long as you needed to. But because cell to fire now operates so rapidly that you could run your initial run on cell to fire to find out what number of iterations should you run across the landscape to achieve that kind of balance. And then you can say, okay, make up a number right now, but say, okay, 60,000 iterations is where I seem to see that. Now you can say, okay, because cell to fire is running 30 times faster than the old system, like now I know how many numbers to give it to Prometheus now, and now I can run it into Prometheus, and I'm pretty confident that I'll get a good number in this. There's no perfect solution to this, but yeah, you do want to evaluate at what point do you start seeing less change, and that is highly dependent upon the size of your landscape and the number of fires burning. So no, there is no rule. I can't give you a number saying, yes, 72,821 is the number you should run. It's going to vary for every run.
Perfect, thank you. So we're almost out of time, and I'm usually a real stickler about end time, but I feel like this last question is really great, so I'm going to sneak it in, and we might run a minute or two over. Are runs reproducible, i.e. can you set a seed so that the results are always the same or something? If so, is there any way to continue running more simulations from where you left off without rerunning things? And I think the part to number 2 you've answered, but the first part of the question of reproducibility.
Yes, it is full, like when you've run a scenario, all the settings that go into the scenario, if you were to rerun that same scenario, you're going to get the same output. And therefore, yes, you can, I mean, you can continue. It's not so much that you can continue with it, but what you can do. So let's make up a number right now. So you ran 40,000 iterations, and now I want to do another 40,000 iterations. So I want 80,000 total. You're going to have to put those 2 runs together at the end because they're going to be seen as separate scenarios, but you then could, I mean, post-processing in a GIS, you can combine the information and then do the calculations. Or you could write a transformer in SynchroSim that combines scenarios and adds them together for you so that you can see it all in your output viewer.
Awesome. Well, thank you everyone for coming and joining us. Chris and Leo, if you're willing to, would you perhaps provide your email in the chat for anyone that wasn't able to ask their question during our live recording?
Sure, I will do that.
Thank you. I'm also going to put a bit of information in there about our next webinar. It's going to be on January 12th. We're going to be looking at the record-breaking 2023 fire season with Dr. Piyush Jain from the Canadian Forest Service. There's also a link there to register. So thank you so much, Chris and Leo, for joining us today. Great presentation, and I'm really excited and looking forward to learning more about Burn-P3 Plus and SynchroSim.
Great,
Thank
thanks.
you.
Thanks, everyone.